Hello and welcome back. We are looking at spectral clustering, and what we will do today is continue our discussion on spectral clustering and then see how we can use ideas from randomized linear algebra and randomization in general to scale spectral clustering. But before that we need to figure out the exact algorithm. So we started looking at it last time, so we will do a quick recap of where we are right now, and then we will try to first put down the spectral clustering algorithm in detail and then talk about randomization and other things. Okay, so here is where we were last time. So spectral clustering, so right now we are in this this is the current understanding. So you are given a graph, you are given a bunch of data points, and we are going to treat, at least intuition wise, we started thinking of treating this set of data points as nodes or vertices of a graph, and then there are these edge weights which can depend on some kind of a similarity with respect to if these are data points, and then this would be some kind of an inverse similarity kind of a metric that we defined. So we have this graph, and from this graph we constructed this let us call this graph GVE and some W to indicate weights, and then we constructed this matrix L which is an R V cross V matrix. If the number of data points that we have is n, then we are treating the number of vertices equal to the number of data points. So this would just be an n cross n matrix. And what was this matrix L? This was D minus W, where D is a diagonal matrix, where diagonal entries were just, so Dii if you remember was just sum over j Wij, and W of course is the weight matrix itself. And then why is this matrix L useful for us? Because we said that the way we are going to do the clustering into two parts is as follows. We would solve the following problem, F transpose LF, and we want to find that F in Rn or R cardinality of V such that norm squared of F is 1 and F transpose the all ones vector is 0. So, so the reason why we wanted to do this was to say that we did not want all the entries of F to be assigned to cluster 0. So we said that we will ground the length of F that we want to be 1 or length squared to be 1, and we also did not want all the entries of F to be 1, that is they go to the other cluster. So we said that F should be orthogonal to 1, and we said that you solve this problem, you get an F star, and then you threshold F star at some 0.5, let us say, and everybody greater than 0.5 becomes one cluster, and everybody less than 0.5 becomes another cluster. That is one way to do it. Or you can take the values of F star, and now it is like all the data points have been mapped to a one dimensional space, so to say, where this one dimensional number for each data point is given by that particular component of F star vector, which is an n dimensional vector. So where each dimension, you can think of it as one number that corresponds to each of these data points. And what you then do is you kind of, once you have mapped it to one dimensional, the real line, the question is where do you put the threshold essentially, and something like a k-means can be run to get that threshold also. So that is how one might want to divide my data set into two clusters. Now so this is so there's a couple of questions here. So how do we solve this problem is the first question. I'll talk about that, and then we will talk about so first question is how to solve this, how to solve. The second question is what if we need k clusters instead of just 2, right? So what do we do if we need k clusters? Well, the first question, how to solve this, depends on how easy is this problem, right? So if you remember, when this F was in 0, 1 power n, That is, if we wanted kind of a hard assignment of data points to cluster 0 or cluster 1, then this was a hard problem to solve, right. So, this was an NP hard problem, I said, which means that we do not expect efficient solutions for that problem. So, we relaxed it and we said we allowed f to be any vector in Rn, and now we are asking, well, because of this relaxation, has this problem become any easier? And the answer to this is yes. In fact, the solution to this is something that many of you might already know if you have especially taken the MLT course and you have seen quadratic forms and so on. The solution to this is just the f star is the eigenvector of L corresponding to the, well, second smallest eigenvalue, that is sometimes called as lambda 2, because lambda 1 is usually the smallest. Well, what is happening here? So, let us say if I had solved this problem without this constraint f transpose 1 equals 0, then basically then what I am asking is, well, I have f which is in a unit circle, and then I want to know which direction in the unit circle gives me the largest f transpose LF quadratic form, and that so the smallest f transpose L quadratic form, and that is equal to, you know, the direction corresponding to the smallest eigenvalue of the matrix L. Now, the question is, what is the smallest eigenvalue of the matrix L? Again, we are talking, remember, we are talking without the constraint f transpose 1 equals 0. So, the smallest eigenvalue would be eigenvalue 0, right. So, the smallest eigenvalue, let me note this down, smallest eigenvalue of L is 0. So, L is what is called as a positive semi-definite matrix, which means the eigenvalues are all greater than or equal to 0, and in fact, it is exactly positive semi-definite because there is an eigenvalue with vector whose eigenvalue is 0. And what is this eigenvector? Well, and the corresponding eigenvector. So, can you guess what the corresponding eigenvector would be? This is a good time to pause and think about this. Let me tell you what the corresponding eigenvector is. The corresponding eigenvector is the all ones eigenvector, all ones vector. Well, why is this true? This is true because it is not too hard to see. Well, what is L? L equals D minus W. That is, if I write this L as an n cross n matrix, and then if I just look at the first row of L, right. So, the 1 comma 1 entry is just going to be sum over all, you know, j W1 j, and then we have W, and then there is a minus W here. So, this is going to be minus W12 minus W13 till minus W1n. And now, if I have 1 1 1 1 1 all ones vector here, n dimensional vector, and see what I get. Basically, you know, this is going to be this sum, and then I am going to just add these things up, and then that will be the remaining, because there is a negative sign that will get cancelled, and then this will just be 0, right. So, basically what is happening is the smallest eigenvalue of L is 0 and the corresponding eigenvector is 1. So, now what we have then done is, in our problem here, we are asking for that direction which is going to give us the smallest value for f transpose LF, but then it is orthogonal to the eigenvector corresponding to the smallest eigenvalue, right. So, now that would just be the eigenvector which is the smallest, has the smallest eigenvalue in the subspace which is orthogonal to the all ones vector, and that would just be the, you know, the eigenvector corresponding to the second smallest eigenvalue, which we call as lambda 2. So then essentially what we have done is we have reduced the problem of clustering to an eigenvalue computation problem, or an eigenvector computation problem rather, right. So because f star is what we want, right. So once we have f star, then we kind of do the thresholding of the components of f star, right. So that's how we get the clustering itself, which is interesting because now we are in the terrain of linear algebra, and then we know how to make things faster in general when we are talking about linear systems of equations and quadratic forms of matrices and so on and so forth. We will talk about that, but that's the idea, right. So this is why it's called as a spectral clustering algorithm, because when I say spectral, what I mean is just the eigenvalues and eigenvectors get involved, and the matrix that for which it gets involved in this case is this matrix L, which is D minus W, and this matrix is important, and this matrix has a name. This matrix is called the Laplacian matrix, right. So far the spectral clustering algorithm, given a bunch of data points, if you would want to divide that into two parts, two clusters, then we construct the Laplacian, obtain the second smallest, obtain the eigenvector corresponding to the second smallest eigenvalue, and then threshold it appropriately to get the two clusters. So that's how to solve this, and eigenvector computation is not it's not exponential time, it's polynomial time, which might be prohibitive if n is large and so on. Nevertheless, it is polynomial time. So it's not an unsolvable problem. It might be computationally expensive, but it's not computationally hard, right. So that's the point I'm trying to make at this point. Okay, so now the second question is, what if we need more than 2 clusters, that is if we need 10 clusters, 5 clusters, right. So in general, if we need k clusters, then how do we solve this problem? Well, the way we will do that in practice is as follows. So you have these data points, of course, you have a bunch of data points, however these data points are. Earlier what we said is we do this mapping of all these data points to the real line, right. So to the real line, so the data points become points on the real line, and how do we get this mapping? This mapping is via our f star, second smallest eigenvalue, right. So it is like a one-dimensional embedding of my data points. The original data points can be in whatever dimension, Rd, right. So this is a one dimension, one number that is enough for me to cluster these data points into 2 clusters. That's what this means. So in general, what we could do and what is done in practice is the following. Use k dimensional embeddings. That is, your second eigenvector of the Laplacian gives you some information, right. So it tells you how to split the graph into 2 parts, splits the data set into 2 clusters. Now, instead of just relying on the second eigenvector, we can go further down and see what happens if I use the third eigenvector, if I use the fourth eigenvector, and so on and so forth, right. So I can go all the way up to k eigenvectors, or k plus 1 eigenvectors if I need k dimensional embeddings, right. So then what I do is, I have this Laplacian matrix L, which is the same D minus W, and then I do an eigen decomposition, and then what I get is F1, which corresponds to lambda 1 equals 0. That is we know what that is actually, we know that is just the all ones vector, and then we have F2, which is the eigenvector corresponding to lambda 2, and we will have, in fact we will have n orthogonal eigenvectors, right. So because we are in an n cross n matrix, L is an n cross n matrix, so this would be Fn, but then we stop at Fk, right. So now the kind of intuition is that each of these vectors is giving us one way to cluster this data into two parts, right. So, roughly you can think of it that way, right. So, each embedding is giving you it's capturing some clustering behavior of this data set. Now, what we would want to do is, I mean, what people do in practice is they do not stop with just one. I mean, you can either use F1 or you can leave that. So, you can go maybe to Fk plus 1, that is a matter of choice. So, what you can do is, think of this as the data set x1 to xn, right. So, remember, each of these guys x1 to xn is in Rd. Originally, they might be in some huge dimension, but then these eigenvectors, the components of these eigenvectors, now if I view them as an embedding for x1, now what I have done is I have taken x1 and then I have mapped it to f1's first, I mean, let us forget f1, right. So, because that is just going to be 1, let us take f2. So, let us say f21, f31, f41 till fk plus 1 1. What is this? This is a k dimensional embedding of my original d dimensional vector. Now, each of these eigenvectors intuitively, right. So, the intuition is that each of these eigenvectors is telling me one different way to partition my data set into two parts, right. So, you can think of it as a view of the entire data set, right. So, how should I partition it into two parts? Now, what I am saying is I am collecting all these views and then thinking of that vector of views as my k dimensional embedding. So, this is in Rk, where k might be 5, 10, whatever number of clusters that we want, whereas d might be 10,000, 1 million, whatever dimension the original data is in, right. So, every I then becomes this, right. So, becomes a k dimensional vector. Now, the hope is that, those data points which really intuitively from a human point of view, let us say, have to be in the same cluster, they have similar views given by each of these eigenvectors. That is, in this view space, right. So, if I think of these eigenvectors as views, one way of viewing the data, then in this view space, points which may not be necessarily close to each other in the original d dimensional space, but then if they are viewed using these eigenvectors values, in this view space they will be closer to each other. That is the hope, right. So, which means that, I mean, I do not know. So, maybe points you might have data set like this perhaps, and maybe you have a data set like this. I mean, this is just, let us say, the data points, and now what could potentially happen is, let's consider 2 points here. Now, these are closer in the original 2-dimensional space R2, but then maybe I take the eigenvectors, right. So, the eigenvectors are giving me different views, and then in the eigenvector space, let us call this point u, let us call this point v. Now, if I take a 2-dimensional eigenvector space, maybe all these gray points, I have not done the computation, but I am just trying to, give a rough intuition here. Maybe all these points end up somewhere here, and all these points perhaps end up somewhere here. The idea is that, instead of using just a single eigenvector, we use multiple eigenvectors. Each of that gives us a different view of clustering the data, and then points which have similar views end up in similar regions. And once that happens, then I can invoke my k-means hypothesis that, these in the view space, the data points are in Voronoi regions. And so, what I can do is, I can run k-means on the k-dimensional embeddings. right. So, this is what people do in practice. I mean, this is one thing that people do in practice, where you compute the eigenvectors top or rather the bottom k or k plus 1 eigenvectors, and then think of each row of this eigenvector matrix as an embedding of the corresponding data point, and then do your clustering on this space. Sometimes in practice what people also do is, before doing this, they would normalize the view space vectors to have length 1, right. So, normalize embeddings to have length 1. That is, what you do is you start with some x in RD, you map it to let's say xi in RD, f1i, f2i till fki. Well, you can ignore the 1 and use k plus 1, that's a matter of choice. So, now then you do the following, you let's call this vector fxi to indicate that this is the view dimensional vector, right. So, this is in Rk, and then what you do is you do fxi divided by norm fxi, right. So, let us say this is my let us call this vi, right. So, this is in Rk, I am setting vi to be this. Let me not, after this we will set vi, define vi like this, that is, we are normalizing the each of these vectors to be of unit length, and now that just means that our embeddings, right. So, the data points can be anywhere, but what I am doing is I am embedding them on a circle, right. So, the data points get mapped to circle, and the hope is that within the circle you have the data point goes to Voronoi region such that a simple k-means algorithm can separate them into enough number of clusters. So, this is the full-fledged spectral clustering algorithm, spectral clustering. Again, there is a lot of caveats here. So, this is using what is called as an unnormalized Laplacian. So, there are other versions of the Laplacian matrix than that one typically uses in practice also. So, the one that we have been talking about is what is called as an unnormalized Laplacian, just d minus w. But if sometimes what happens is this algorithm may not work that well if the clusters do not have balance. That is, you might have 10,000 points in one cluster in the natural way of clustering them, but then you might only have 20 points in another cluster, right. So, there is a balance mismatch, and in those cases this just using the Laplacian may not usually work. So, what people do is they do like a so I mean naturally the cuts are going to basically the intuition comes from cuts, right. So, and then the values of the cuts are going to be completely different if the number of nodes on each side is completely different, right. So, so this is called as a normalized cut intuition that one can start with, and if you start with the same intuition that we had of the cut, and then that ended up in Laplacian by doing a relaxation, and that ended up in an eigenvalue problem using a relaxation. So, now you can ask for a normalized cut. So, you can ask for dividing the data set into two parts, the cut, but then the cut size should not be should be balanced, right. So, that then the ratio of the number of data points that end up in each of these cuts have to be within some bound. If you start with a different constraint like that, you will end up in a different eigenvalue problem for a different Laplacian. The problem is the same, but then the Laplacian that we would end up for which we would end up computing the eigenvectors and eigenvalues will be different, and that is sometimes called as a normalized Laplacian. But that's what people sometimes do in practice. But then the idea that I am really trying to get at is we can start with a graph cut intuition, and then we can go to relaxation, which is a simple eigenvector problem, and now you can think of eigenvectors as giving you one view of your data, and then put all the views together, and then just to get the scale intact, you can kind of normalize it and then bring all the data points as embedded in a hypersphere of k dimension, and then run k-means on this new embedded data. And that will give you a clustering, right? So, because k-means is going to say which point goes to which cluster, and then of course, this is in the view space, but then there is a data point for which this is in the view space. We will assign that data point to the corresponding cluster, right? So, for example, in this case, some data points have views here, some data point has view space here, correspondingly we will cluster those data points. So, that is the basic idea of spectral clustering. Now, so this is the first part.